Throughout AP Physics 1, we've described how motion works through the science of kinematics, and then we've described why objects move the way they do through a couple of different lenses. 1 talking about forces, 2 talking about momentum, and 3 talking about energy. Well, now we're going to take all of the ideas we've talked about this year and start to explore how they apply to a couple of different specific types of motion. And then the first one of these units that's a little more specialized, we're going to be focusing specifically on rotational motion, or in other words, how things spin. But before we get to the why, we really need to talk about the how. How exactly do we describe something that is moving? And specifically, we're going to start describing how is something rotating. And we're going to do that by looking at kinematics once again, but this time rotational kinematics. So first, let's just have a broad definition of what rotation is. So rotation is when an object spins around an internal axis of rotation. So if I have this sphere here, it is spinning in essence around itself, around this internal axis. Now remember, this is different from what we did in circular motion, which had to do with revolution, with the idea that objects are moving around an external axis of rotation. Now they're spinning around an internal axis of rotation. Now, a couple things here is that we want to be careful of whether we're talking about the object itself or points on the object, because the entire object is spinning, so on the whole it is rotating, but if we look at one point on the object, well, that point is going to be revolving around this axis of rotation, so we just need to be real clear about what specifically we're referring to. And additionally, just as kind of a quick note, we're going to be dealing with what are known as rigid objects, for the most part. What we mean by that is as they rotate, they do not change their shape. So it's not going to be like, for instance, you've all seen this, for instance, like pizza dough, which is if you have a ball of pizza dough and you spin it, it flattens out into a disc. That would be a non-rigid object. We're not going to focus on that. We're going to look at objects that are maintaining their structural integrity. So just like we did at the beginning of the year, let's start real simple. How do we define not only the position of an object, but its change in position, specifically with rotational motion? So let's say I've got a couple points on this object that I've labeled here A0 and B0. This object on a whole is like a circle. And if we rotated this object, this position would now be here, this one would now be there, but how do we quantify this change in position? And you might think, well, we could do the distance that both of these points have traveled in whatever this time interval was. But the thing is, though, is if we do that, we're going to notice that the distance that point A went through and the distance that point B went through are different. That ultimately, as the whole object rotates, points that are closer to the outside of the object are technically covering more distance than points closer to that internal axis. So if we want to describe how the entire object is rotating, distance is not enough because we wouldn't necessarily know where to even define that. So instead, what we could look at is the angle. The entire object, every point on the object, moves through some angle going from one position to another. And this brings us to the idea of angular displacement, or delta theta, which is just a change in angular position, so final minus initial. And angular position is just a location around this axis of rotation. Now, typically speaking, we can define our zero, and we would say that the positive direction goes this way, and the negative direction goes the other way in this rotation. So for instance, this would be positive delta theta. If we did 3 times that, we would go through 3 times the angle, and the whole object would have shifted to here. In essence, what this is saying, the angular displacement, is the angle that a point on an object moves through. If it goes through 20 degrees, the entire object has rotated that much. Now, something to keep in mind, though, is that means it is the same for every point on the rotating object. And this is why it is so useful. This is very crucial. We want to describe the entire object's rotation with one single value. That is why we use angular displacement rather than some linear value. So what are the units we're going to use for angular displacement? Well, we can do this in a few different ways. One, we could do the number of degrees it goes through. We could do the number of radians it goes through. Or we could say, well, what is the number of rotations? For instance, 1 rotation, half a rotation, third of a rotation, etc. And we can convert between the 3 of these by remembering that 1 rotation is equal to 360 degrees, which is equal to 2 pi radians. And I'm going to go ahead and tell you that in this class, we're pretty much going to focus explicitly in radians. And this might be surprising because we spent the entire year talking with degrees, but we're going to see why that is in just a second. For instance then, we need to make sure we can convert from rotations in degrees to radians. So let's say, for instance, we had two objects and one rotated with 2 1/3 rotations and one rotated by 85 degrees. How could we put both of these values into radians? Well, for the 2 1/3 rotations, well, it's pretty straightforward. We usually remember that one rotation is 2 pi radians, so we just multiply 2 1/3 by 2 pi, and we get 14.7 radians. Now, I could have said instead 2 times 2 1/3 would be what, 4 2/3? So I could have said 4 2/3 times pi radians, but that gets really, really sloppy. I'm going to contain it all into a single value of 14.7 radians. And then for 85 degrees, I'm going to do the same sort of thing. I'm going to get 85 degrees to number of rotations by dividing it by 360 degrees. And then I'm going to multiply it by 2 pi to get into radians, and I get 1.48 radians. Once again, I'm avoiding using the pi there. Radians are something very specifically physical, so getting the pi out of there is going to help me think about what really this number is telling me, and we will talk more about that in class. So let's take a second and think about something. Let's say we had a wheel, and this wheel was going to start rolling, and this is its radius r, and we'll say initially this is position delta theta is equal to 0, so it's not been rolling at all yet. And we're going to have it start rolling, and let's kind of see if we can quantify a few different things. One, the number of rotations it goes through, equal that to the number of degrees in radians, and additionally, the linear distance that this wheel is going through, or in other words, the distance that this point on the edge of the wheel will be covering as time goes on. So let's say the whole thing rotated so that it's gone through 1/4 of a rotation. Well, 1/4 of a rotation is 90 degrees, and in radians that's pi over 2. Most of you probably have that memorized from your pre-calc class. Now, if we were going to do the linear distance this has gone through, how could we figure that out? Well, an entire circumference, if this whole thing went through one whole rotation, this point would go through 2 pi times r, the circumference of a circle. But we've only gone through 1/4 of that, so we want to divide that by 4. So we're left with that went through pi over 2 times r meters, we'll say, for instance. And let's say this rotated even more, so now it's gone through a total of a half rotation. And if it's gone through a half rotation, it would be 180 degrees. That would be pi radians. And that distance would once again be the circumference, or 2 pi r, divided by 2, so just pi r. Okay, well now we think we might be seeing a little bit of a trend here. So let's say I went through a full rotation. If we went through a full rotation, it would be 360 degrees, 2 pi radians, or a linear distance of 2 pi r. And if it went through 1.5 rotations, that would be 540 degrees, 3 pi radians, or a linear distance of 3 pi r. And what we notice is there is a definite similarity between the number of radians and the linear distance this point has gone through. And in fact, we can relate them together by saying the linear distance delta x of this point on the wheel is equal to the radius of the wheel times delta theta, the angle the wheel has gone through, specifically in radians. Not in degrees, not in number of rotations, but in radians. And this is really the reason why we want radians specifically. So how do we move between a rotational regime and a linear regime? And really what we mean by that is, how do we move through the angle that an object has rotated through and the distance that points on that object have traveled through? And that is through this relationship of delta x is equal to r delta theta, where delta x is the linear distance. Distance is a better term here than displacement in meters. R is the radius in meters, and delta theta is the angular displacement in radians. Now you might be thinking, how does this work out? Radians is actually a unitless unit, which kind of sounds a little weird. It's really more of just a ratio. Once again, we'll talk more about that in class. So you don't technically have to write radians. You could just leave it blank. We'll discuss that more. But the thing is, though, is we need to remember that this delta theta is telling us how much the entire object is rotating, and the delta x is telling us the distance that a point on the object is moving through. So if I was looking at a point on the edge here, well, then I would use this whole r. But if I was looking at a point here, I wouldn't use this whole r. I would find a new r. I'm just going to say that's r new. And that would be the radius I would use, so that when this object rotates, I would know the distance this point has moved through. But now that we've talked about position, how can we discuss how quickly an object is rotating? And that is through something known as angular velocity, which we abbreviate with this is a lowercase Greek letter omega. It basically looks like kind of a curved W. I've had some of my students before call it W. Doesn't matter to me, but it is an omega. And this is the rate at which angular position changes with respect to time, exactly like regular velocity and regular position. So we get that omega, the angular velocity in radians per second, or we could just write that as 1 over seconds, is equal to delta theta over delta t, where delta theta must be in radians, and delta t must be the change in time in seconds. And you may not be very familiar with angular velocity in this way, but you've actually learned about it before, whenever you've dealt with something dealing in RPM, rotations per minute. Now, that was not in terms of radians per second, but it was still an angular displacement over a change in time. So RPM is a form of angular velocity, or how quickly something is rotating. It's just not the units we're going to be using here. Now, one thing we want to keep in mind is that, once again, because delta theta is the same for every point on the object, that means omega, or angular velocity, is also the same for every point on the rotating object. So if one point is rotating at some rate, then every other point is rotating at that exact same rate. Lastly, and as we mentioned earlier, we define angular velocity, typically speaking, in terms of the clockwise and counterclockwise direction. But for math's sake, you need to make one of those positive, one of those negative. Typically, convention puts counterclockwise as positive and clockwise as negative, because that's the direction positive and negative go with the unit circle. But how exactly can we move between angular velocity and regular or linear velocity, just like we do angular displacement and regular displacement? Well, we can kind of look through our regular velocity equation, which is v is equal to delta x over delta t, but now I can substitute in for delta x r delta theta, and I can pull that r out, because that r, that radius, is a constant. So now I have r times delta theta over delta t, but delta theta over delta t we just defined as omega. So to move between the linear and rotational regimes, again, we just multiply it by r once again, where v is the linear velocity in meters per second of a point on this object as it rotates, r is the radius in meters, and omega is the angular velocity of the entire object in radians per second. So let's look at a brief example. Let's say myself and my dog Lucy are on a spinning merry-go-round that rotates 3 times in 8 seconds. And we can see here that this is an overhead shot. It's going in the clockwise direction. Lucy is 1.2 meters from the center. I am 2.4 meters from the center. And what's the angular and linear velocity of both Lucy and myself? Well, let's start with the angular velocity. Well, the angular velocity is going to be the same for both of us, because the entire object has the same angular velocity. It's all rotating at the same rate. So I'm going to say omega of myself and omega of Lucy, they're the same thing, is equal to delta theta over delta t. Well, it's going 3 times around, so that would be 3, and I need that in, that's rotations, I need that in radians. So I would do 3 times 2 pi radians over 8 seconds, and we get an angular velocity of 2.36 radians per second. Or, to be even more precise, we would say 2.36 radians per second clockwise, or I could say negative 2.36 radians per second. What about our linear velocities? Well, our linear velocities, we just take those omega and we multiply it by our respective r. So Lucy has a linear velocity of 2.83 meters per second, and I have a linear velocity of 5.66 meters per second, meaning I am covering 5.66 meters of space every second. She's only covering 2.83 meters of space every second, because she is closer to that axis of rotation. So we talked about displacement or change in position. We've talked about velocity, or that change in position with respect to time. What if that rotation rate is speeding up or slowing down? In other words, what if the rotation is accelerating? And that's when we come to this idea of angular acceleration, which we abbreviate with what is here a lowercase alpha. So this is alpha. Basically, it looks a lot like the Jesus fish. It's not the Jesus fish, but it looks a lot like the Jesus fish. And this is the rate at which angular velocity changes with respect to time. In other words, is the angular velocity increasing or decreasing? Is the object's rotation speeding up or slowing down? So that's delta omega over delta t, where angular velocity is in radians per second, delta t is in change in time in seconds, and the angular accelerations is radians per second, otherwise known as radians per second squared. And once again, this is the same for every point on the rotating object. And it's probably not that surprising that once again we can move between the angular and the linear regimes by just multiplying by r once again. If we start with our angular acceleration, or alpha, remember that's how quickly the object's rotation rate is speeding up or slowing down, and we multiply it by r, the distance to some point on the object, which could be the entire radius in meters, and then we get what is known as the tangential acceleration in meters per second squared. And that's how quickly a specific point on the object is speeding up or slowing down. Now, one thing I want to note here is there is actually another type of acceleration we've learned with sorts of motion like this, aka centripetal acceleration. We will talk about how that relates to this in class, but this is a different type. This is talking about speeding up and slowing down, not direction change. And just like I said at the beginning of this video, a lot of the concepts we're going to talk about in this unit are things you've learned about before, but you learned about them in what is known as a linear or often a translational regime, talking about objects moving side to side, up and down, diagonal, what have you. And now we're going to take these same concepts and morph them into an angular or a rotational regime. In other words, how things are spinning. But the physics is ultimately the same. So let's start creating a table in your notes. I would make a table just like this. In fact, I would make this a whole page because we're going to keep adding to this over time. And the first thing we're going to say is, okay, the displacement for both of these is delta x in linear and delta theta in angular. And we move between these by saying, well, if I want to get from rotational to delta x, I multiply it by r. And if you went the other way to get delta theta, you would divide delta x by r. Okay, now going to velocity, linear velocity is v equals delta x over delta t. Angular velocity is omega is equal to delta theta over delta t. And we can once again move between these by either multiplying by r or dividing by r. And then we can go even a step further with acceleration, with specifically tangential acceleration, which is delta v over delta t. And alpha is equal to delta omega over delta t. And we can move between these by once again either multiplying or dividing by r. But let's say we had certain pieces where how can we start combining displacement, velocity, and acceleration into specific equations? And we can do that through the use of kinematic equations. The kinematic equations are four equations that, remember, we can only use when the acceleration, or in other words, the a or the alpha, are constant, but they allow us to figure out some pieces that we don't have, relating these three variables to time. So you knew all of these in the linear regime. These are the equations that are in your notes. I can now move to the rotational forms of the kinematic equations by substituting v with omega, delta x with delta theta, and a with alpha. But the science is exactly the same. So now I have omega is equal to omega naught plus alpha t. Delta theta is equal to omega naught t plus 1/2 alpha t squared. Delta theta is equal to 1/2 omega naught plus omega times t. And omega squared is equal to omega naught squared plus 2 alpha delta theta. Exact same science, just a new way of looking at it. And to give an example of how these kinematic equations work, functionally exactly the same, let's look at a practice problem. Let's say we have a wheel with a radius of 60 centimeters that initially spins within an angular velocity of 7.5 radians per second. In other words, its rotation rate, how quickly it's rotating, is 7.5 radians per second. It speeds up at a rate of 4 radians per second squared for 5 seconds. And we want to know what is the wheel's angular displacement during these 5 seconds. If the wheel was rolling, how much distance did it cover? And how fast is the wheel rotating after the 5 seconds have passed? So, okay, how exactly do we go about this? Well, we could use the guess method. And the first thing we do in the guess method is we identify our givens. Well, what are we given? A wheel for radius of 60 centimeters, well, this would be r. Specifically, it would be 0.6 meters. We need it in meters. Angular velocity, this is the initial angular velocity. Omega naught is 7.5 radians per second. A 4 radians per second squared is our angular acceleration, or alpha. And 5 seconds is my time, or change in time in seconds. And we want specifically, let's change the colors up a little bit, we specifically want the wheel's angular displacement, so we want delta theta. We want how much distance does it cover, so really that is asking for delta x, specifically at the edge of the wheel, and how fast is it rotating after 5 seconds, we want omega. So let's first do this first one, looking for delta theta. I would use one of the kinematic equations, specifically the one that involves omega naught t, alpha, and delta theta, and I would substitute in. So I have omega naught times t plus 1/2 alpha t squared, and I get that the entire wheel has gone through 87.5 radians during this 5 seconds. Now let's look at the next one. Well, the next one is the amount of distance it's covering. So we're moving from a rotational regime to a linear regime, and I can do that by just taking my delta theta and multiplying it by r, which is the distance to this point, which is 0.6 meters, and we get that that entire wheel, or a point on the edge of the wheel, has gone 52.5 meters during this 5 seconds, or in other words, the wheel would have rolled a distance of 52.5 meters. And lastly, we look for omega, or the final angular velocity. We could use omega is equal to omega naught plus alpha times t. We substitute in our values, and we get that the final angular velocity after these 5 seconds is 27.5 radians per second. So that's how quickly it's rotating now after these 5 seconds have passed. None of this is different. You find your givens, your unknowns, you identify an equation, you plug in values, and you solve. It is all the exact same science. We're just using new, potentially scary words. But everything else is exactly the same. So what are our key takeaways for this first lesson on rotational motion, focusing on rotational kinematics? 1, can we describe the change in position of an entire rotating object using this concept of angle, or delta theta, rather than focusing on the distance specific points go through? Can we calculate how quickly an object is rotating and how quickly this rotation rate is changing? So basically calculating the angular velocity, or omega, and the angular acceleration, or alpha. Can we move between the linear and rotational descriptions of motion, or in other words, how something is rotating and how points on that object are moving through space, remembering that to get from one to the other, specifically from rotational to linear, we multiply by r, and crucial here, it must be an angle in radians. If it's not in radians, we cannot do it. So we're using radians explicitly when we're doing things like this. And then lastly, can we use the rotational form of the kinematic equations using our guess method and everything we've learned previously, just substituting in new symbols and words to describe these new types of problems, but the science underlying it all is exactly the same.